welcome you to the course on defects in materials. Okay. In the last class, we have discussed about the forces which are acting between dislocations and also in the presence of an external field or external stress. Okay. What is the direction in which the force will be acting on the dislocation? This we have looked at for a pure screw and a pure edge dislocation, correct? And what we will do today is that at that time when we looked at these defects in material, one important thing which was there was that when we looked at the force on a screw dislocation, we had one component I sigma YZ into BZ J. These are all, both are shear stresses. Okay. So this force on screws can be written as nothing but I into Fx plus J into Fy. Correct? These are all the components in the x and y direction. But if you look at the components in the x and y direction, it's essentially a shear stress which is acting on the dislocation. Whereas when we derived an expression for the force acting on a edge dislocation, okay, in this case it is so in this one, if you look here, this is a shear stress, the application of the shear stress that develops a component of a force is I into Fx, that's force in the x direction, whereas the tensile stress which is being applied to the material, that generates a force essentially in the y direction, correct? Y direction means that x direction is where that slip plane, slip direction is there, this is perpendicular to the slip plane, a force is generated. Okay. This doesn't happen in the case of a screw dislocation, it's only a shear force which is coming, whereas here we have a force which is perpendicular to the slip plane is coming. That is, if a edge dislocation has to move in that direction, the first thing which has to happen is that some vacancies have to be generated. Okay. What will be the consequence of these vacancies? And this itself generates a force which is called as a chemical force. This is what we will discuss in today's lecture. Okay. So here what I have done is I had just shown the two-dimensional lattice, okay, with a vacancy as well as an interstitial. This is what we call it as a generally as a Schottky defect. We can find out the concentration of the vacancies which are going to be there, because earlier when we derived the equilibrium concentration of vacancies, we assumed that the material contains only point defect, correct? That is the way we did it. But normally the material always contains dislocations, okay, and dislocations and vacancies both are present and they are in equilibrium, okay. If we apply a stress, okay, like any tensile stress if we apply to the material, okay, then vacancies can be generated, correct? The derivation which we are going to follow, we make an assumption that the vacancies which are generated by the moment of the dislocation, okay, they can annihilate only at the dislocation. That is, the vacancies cannot escape out of the sample surface. This case can happen in real materials when we consider temperatures below 0.5 Tm. Vacancies may be mobile, but the excess vacancies which are being produced, okay, the mobility is not sufficient for them to come out of the sample surface. We can consider that as one particular case where this sort of a situation can happen. Here we make an assumption that whatever the vacancies which are produced by dislocation moving up or down, vacancies which are produced or annihilated, Okay. These vacancies, the sink also is only the dislocation. Okay. That's the assumption under which all these derivations are being done. Okay. This picture essentially shows that in the absence of a stress which is being applied, the vacancies and dislocations are in equilibrium. Let us, physical picture we will try to have, then we go into the mathematics of it. Okay. And if we apply a tensile stress sigma xx, as we mentioned in the last class, okay, when a tensile stress is being applied, in the case the extra plane will try to come down. If the extra plane has to come down, means essentially it is equivalent to some atoms from the bulk of the material come to the end of this dislocation, okay, and join together here a row. That is way the dislocation, this will be equivalent to the dislocation line going down, correct? This is exactly what will happen. So if that happens, when an atom has been removed from the lattice, vacancies are created. Now the dislocation is under the action of this force. This force, the expression is already given by this equation, that this force Fy is equal to minus sigma xx into B, correct? That information is already available. So as the dislocation comes down, okay, when the vacancies are created, these vacancies will try to generate, because if they are not going out of the sample surface, this is going to generate a pressure inside the material or some sort of a force. That force will try to act in a direction which is opposite to the direction in which the external force is acting on the dislocation. When these two forces become equal, then the dislocation will no longer move. Okay. So essentially what happens is that lots of dislocations will be generated in the material by non-conservative motion of dislocations. Okay. This is essentially what is being written here. Now, what is the methodology which we follow to find out the stress which is going to be generated, okay, by the action of an external stress? What is the concentration of the vacancies which will be generated? These are all the information which is required. The concentration of vacancies which are generated in the on applying load. Okay, that's what we are trying to look at it. Okay, we know that under thermal equilibrium condition, when no external stress is being applied, the free energy change which is going to take place depends upon the energy which is required for formation of a vacancy, for a single vacancy. Then SV is essentially, the T into SV is the entropy term, okay, the contribution due to entropy energy, where SV is both corresponding to the change in the vibrational energy plus the configurational energy. Okay. Since lot of vacancies are there, creation of each vacancy, okay, some volume is being added to it. That is what we have added as the VV, is essentially nothing but the volume of the vacancy. One should understand this volume of this vacancy is different from the size which an atom is going to occupy in a lattice site, because there is some relaxation is going to be there, so it's not that same. Okay. So at equilibrium, this is how the value will turn out to be, correct? This expression we have derived in the case of a point defect earlier. Okay. When we derived for the point defect, at that time we did not consider this part is P into V, is essentially nothing but a mechanical energy. This is internal energy change, this is the entropy change, this is the mechanical energy change. These together decide the free energy change, correct? So here if we now try to look at it, in this N is the number of atomic sites, Ne into T is the number of equilibrium vacancies which are generated, okay. The Pe is the equilibrium pressure which is there, the normal pressure, okay. All the terms have been explained earlier now. What will happen under the application of a stress? Okay, when we apply a stress, by the mechanism which we talked about earlier, lot of vacancies are going to be generated in the sample, correct? When vacancies are generated in that sample, okay, now the concentration of vacancies is more than what it should be, okay, when the stress is not applied under thermal conditions, right? And these excess vacancies, they are going to, the volume per vacancy we know. So because excess vacancies are created, there is going to be a hydrostatic pressure which is going to come in the material, okay. These are all the terms essentially which is coming into the picture, okay. This is with respect to when a stress is being applied, okay. If you take the difference between these two, okay, free energy change, this will give the change in free energy which is occurring as a result of application of mechanical stress, correct? That free energy change, if we take the difference between the one corresponding to under the action of the stress, okay, and one in the absence of stress, this difference will turn out to be kT into log. N sigma T is the vacancy concentration on application of load. This is the equilibrium vacancy concentration at the same temperature, okay, and P sigma minus P is the one which is under thermal equilibrium condition. This is corresponding to the stress which is going to be, this is the hydrostatic pressure, okay, when the load is being applied. The stress which is being applied is this hydrostatic pressure. This we can write it as P equals P sigma, okay. This will be right. We know this expression, the hydrostatic stress. So P sigma minus P can be replaced by P and we can write it, okay. So this tells us what is going to be the free energy change, okay, which is occurring because of the generation of excess vacancies due to movement of dislocations. As far as what we consider, so this should be equivalent to, if you have, when we know the external stress, okay, that has been, this is Fy, okay, this is essentially nothing but the force per unit length of the dislocation, okay. This will be essentially equivalent to the work which is being done to move a unit length of dislocation, right? Under the action of this, the dislocation is moving in which direction? The dislocation which is being present is moving from here to here, correct? So let us consider one atomic displacement of the moment of the dislocation if it is taking place. That means that one row of vacancies has to be added to it. Or even if at one atomic site, if a dislocation has to climb down, correct? One atom has to be added to that site, okay? Then only the dislocation will climb down, okay? Or if a dislocation has to climb up, okay, one atom has to be removed from that and we have to create a vacancy, okay? One row has to be for a full row, otherwise at one particular point it will be creating a jog essentially. For this to happen, a length alpha b of the dislocation, we assume that for one atom position it climbs, okay, and what is going to be the Burgess vector corresponding to that? Beta b we take it to be. So essentially, if this is equivalent to generating a force on the dislocation, okay, opposite to the force which is being applied for the dislocation to move, that will be equal to that force, we call it as Fc. So Fc into this one will give the energy which is required. So that is what essentially we have written as W equals, okay, These alpha and beta are parameters which will be depending upon the crystal structure, their values can change, okay, and they are mostly close to 1. Okay. In many calculations we take it to be 1 and take, okay, that's how it is being taken. So now what we should do is that we should equate these expressions, correct? That is, this we calculated the free energy change. This is equal to the force which is being applied, okay. So this, then if we wanted to find out Fc, we take it to be under this side. So then we will be getting an expression like this, okay, and this is equal to nothing but the applied force, okay. This is how we can write it, and P, as I mentioned, equals minus 1 by 3 sigma xx. So essentially in the present case the stress is sigma xx, the pressure P will be minus 1 by 3 sigma xx, okay, hydrostatic pressure. So what I have written is that this force, okay, Fc is written, I just written as B, okay, just denote it by B, okay. It does not matter, one can use Fc also as the notation. This force is the chemical force. And what is the direction in which this force will be acting? This Fc equals this B cross U is the line direction of the dislocation. Perpendicular to it, it will be acting. So far what we have considered is 3 cases. One, if we take a dislocation, a straight dislocation line, and if the dislocations are being anchored at 2 points, if we apply a force, the dislocation will bend into this shape, right? Then the force which is going to act will be equal to T by R, which is equal to applied stress into Burgess vector. That's one force which is acting on the dislocation. Other force is that external stress as it is being applied on the dislocation, that generates a force on the dislocation to make it move, okay. That's the applied stress, that is what essentially it is. In addition to it, when the applied stress turns out to be not shear but it is tensile, for the edge dislocation, now we have a force which is a chemical force which is also acting on this. So these are all the 3 forces which are going to act on a dislocation, okay. These 2 forces, that is F equals, due to a line tension Fl plus F applied plus Fc. So these 2 together, applied plus Fc, we can write it to be equal to B plus, or I should write it the other way around, G plus B cross U, correct? But what we should remember is that the chemical force acts only on edge dislocation, because for the chemical force to be generated, okay, essentially a tensile stress which is acting, and the tensile stress has an effect to make the dislocation only an edge dislocation to climb up or down. It has no effect on the screw dislocation, okay. So this one should always remember. So on a screw dislocation, what is going to happen is that it will hardly have any effect. Screw dislocation, only the line tension and the applied stress will be having that effect. What happens in the case of a mixed dislocation? What do you think will happen to a mixed dislocation? Yeah, mixed dislocation, what will happen is that, suppose we have a dislocation which is has a, I just am drawing a cross section of a dislocation, and its viewing direction is, that is, the plane of the dislocation is in this perpendicular to this direction. Okay, this is just the cross section. Suppose we assume that this side, okay, this part of the dislocation, the projection, this is a projection of the dislocation, is an edge component, and these two ends which we see, the part of the, because this is essentially nothing but a dislocation, circular dislocation. Okay, we are just looking at the dislocation from in this direction. Then we will be looking at the dislocation in this way, correct? This is how the line direction of the dislocation is. Okay, then the Burgess vector will be in this direction, okay, of the dislocation. Then this is an edge part of it. Okay, this is going to be a screw component of it. Okay, if we apply a stress, that stress could be a shear stress, or it could be a stress which is a sigma tensile stress, tensile or compressive stress. If we apply a tensile or a compressive stress, then what is going to happen is the edge part of it, depending upon the whether it's a tensile or a compressive, what will happen is that the dislocation may climb up. This process will occur only at high temperatures, where the vacancies are mobile, because at room temperature, though there may be forces which are acting on the dislocation in the y direction, because a tensile stress has been applied, okay, it is mobility of the vacancies is so small that nothing much happens. Only at intermediate temperatures this sort of a process will occur. So essentially when we look at it, which was only a, sort of like this, now we observe that this has bent like this. The edge part is still in the slip plane, whereas the screw part of the dislocation has just climbed up. Okay, this is what essentially will happen in the case of a mixed dislocation. Okay. So in fact, these sort of microstructures which they come, one has to be very careful when one looks at electron microscope. Okay, then one has to identify which is the slip plane, which is the Burgess vector. All the information one has to obtain to get correct information about which is the way this dislocation is moving. Okay. What are the consequences of this sort of generation of vacancies in the material? Okay. We will take one. What will be the effect of this chemical force? Okay, that we are comparing between a mechanical stress which we are applying and the chemical stress which is generated. This sort of a chemical stress can be generated in a material by irradiation. When we irradiate it, interstitials and vacancies are produced. Okay, interstitials can diffuse very quickly to the surface, but excess vacancies will be generated within the material. Okay, if the two options are there for the vacancies, one, the vacancies can go to the surface and get eliminated to reach an equilibrium concentration, or the vacancies can go to the sink which is present within the material, which are dislocations, and the dislocation can climb up or down. That means that these vacancies are trying to put a pressure on the dislocation. Correct? That way we can consider it. But essentially, in this, what one has to look at it is that what will be the sort of a vacancy concentration which will be required, okay, to put stress on the dislocation. Okay, whether very high concentration. If you look at this expression, okay, this B we know for a dislocation in a typical material we can take it. K is the Boltzmann constant, T is the temperature, correct? And N sigma by Nt is this, if we calculate this value, okay, this is in energy, okay, So this will be equivalent to a force which it will turn out to be, and that value turns out to be about mu 20 to 100. Okay, with respect, that is, this value of the stress generally turns out to be in few GPa. Okay, plus you have a log n sigma by Ne is there. This ratio, if we take it, okay, most of the time, even if we take this value to be about something like close to 1 or 2, that is, if the vacancy concentration is raised by just double. Double means that generally at melting point we consider vacancies to be typically around 1 into 10 to the power of minus 4. It is increased to 2 into 10 to the power of minus 4, the vacancy concentration. Just this increase in concentration will be putting a stress which will turn out to be much above the theoretical shear strength. This one can do this calculation and just work out. Okay. That means that even a small increase in vacancy concentration can generate the type of stress even by mechanical force we will not be able to generate. That sort of a stress which generates, which is equivalent to, okay, theoretical shear stress of the material, or much above the theoretical shear stress. Okay. What is the situation in which we will be facing this sort of a stress condition in a material? One of the things which one can think of immediately is, yes, high temperature laboratory. We take a sample, keep it close to a melting point to solutionize the sample. Then we quench the material most of the time to generate, to retain the high temperature microstructure. That's what normally done by solutionizing treatment. Okay. When we do this quenching, what will be the sort of vacancies which are generated close to melting point? It is of this order. If we bring it to room temperature, what will happen? Orders maybe 10 to the power of 6, 10 to the power of 7 or 8. Of that order, vacancy concentration will be produced. No material will be able to accommodate this sort of a vacancy concentration. In fact, what happens in most of the material is that the vacancy concentration is reduced considerably. How that happens is that as the sample is being quenched, okay, many of these vacancies, when they are mobile, they try to come to the surface and equilibrate it. And beyond a particular point, when this cannot happen, these vacancies which are close by a short distance movement, they can agglomerate and form vacancy loops in the material. Okay. This is what I called as the quenching stresses. Okay. So in fact, in most of the material, the best example is that if we take aluminium or copper, okay, it's a very well annealed structure. We take it to close to a melting point and then quench it. Then if we see, we will see a lot of dislocation loops will be there. These loops are essentially Frank loops. Okay. In FCC, okay, on a close packed plane, if vacancies condense on a close packed plane, that means atoms are removed from that layer. This will be equivalent to generating a Frank dislocation, right? So these, in this process, a lot of vacancies have been accommodated and dislocations have been generated in the material. This is what essentially happens. With this, what one will observe is that the concentration of vacancies is brought down considerably. So the consequence of it will be that if we take any material, okay, we quench it from a very high temperature. Okay. When the vacancy concentration comes down, we assume that the vacancies are retained. That doesn't happen. Instead, lot of dislocation loops are generated within the material. Okay. These loops also will generate some stresses in the material. These stresses are what we call it as the quenching stresses. The effect of these sort of stresses where we can see where we don't allow material for expansion to take place or a contraction to take place. Can you imagine can you tell me a situation where this occurs? This is what we call as well cracking. What is a well cracking? Or you weld a material, okay, and just what happens is that after that, when an expansion is going to happen, that there are tensile and compressive stresses which are being generated, quickly we quench it. Then what will happen is that afterwards we say that the crack has developed. So the stresses which can be generated are of this order, very high stresses which could be generated. Similar phenomena, in fact, we can think. Especially ceramic material, if we consider it. Ceramic materials should never be quenched. You know that. If you try to quench it, what is going to happen is that the whole material will shatter into pieces. In the case of metallic samples where it can plastically deform and accommodate, there some dislocations will be generated, but there are cases under situations where we find that this is not able to happen. In such cases, okay, the material cracks are observed. Otherwise, in most of the materials, the quenching itself produces, okay, sufficient dislocations and stresses are generated. That is, if I take a material, the best experiment which one can do to verify this, you take a sample, okay, which maybe is a deformed sample, take it to high temperature, it is annealed, slowly cool it, so that at every instant of time we are allowing the vacancy concentration to equilibrate, okay, and then take some sample which is quenched very fast. If you observe these two samples and try to find out the dislocation density which is going to be there in these two cases, the one which has been quenched, the dislocation density will be very large. Okay. These dislocations, this excess dislocation density, because there the vacancies are getting equilibrated, the concentration. So when it cannot happen, these stresses, only way they can relieve the high stresses which are generated due to excess vacancy concentration is vacancies which are close by in some region, they all come together and condense and a small loop will be formed. That is the way they can generate this, they can relieve these stresses. Okay. This we will observe, this material. Okay. So from this, what we have considered, that is, in all this, the last few lectures, 3 or 4 lectures, what we have looked at it is that what is the force which is acting on the dislocation, okay, the various components which we have considered, okay, one due to a bending of the dislocation and another due to the applied stress, to find out the direction in which the stress, the force is going to act on the dislocation. The Peach-Coiler equation was derived. That's an elegant method with which we can immediately, using that equation, we can immediately find out what is the magnitude of the stress and in which direction the stress is going to act. Then, when excess vacancies are generated in the material, what will be its effect, okay, on generating stresses. And as we discussed just now, these stresses, even in a small increase in vacancy concentration, it is going to generate very high stresses, okay. And what are the implications of these stresses? This is what we have considered in this lecture, okay. In the next class, what we will do is that we will talk about some dislocations in some specific systems which we will consider, okay. Like for example, in FCC, okay, where both perfect dislocations and partial dislocations are going to form. These aspects we will look at it in the next few classes. Okay, we will stop here now.